Hello everyone, I'm Ellie. Today I'll be talking about the working principle of DC generator. Before I start explaining about DC generator, it is an electrical machine which converts mechanical energy into direct current electricity. This working principle of DC generator can be explained using Faraday's law of electromagnetic induction, which states whenever there's a change in magnetic flux associated with a conductor, an EMF is induced in it. Hence, this law can be summarized as the magnitude of induced current is directly proportional to the rate of change of magnetic flux. The magnitude of induced current can be affected by the speed of relative motion between the coil and the source of magnetic field lines, the strength of magnetic field, and the number of turns in solenoid. As I have said earlier, whenever a conductor is placed in a varying magnetic field or conductor is moved in a magnetic field, an EMF gets induced in the conductor. If the conductor is provided with a closed path, the induced current will circulate within the path. In a DC generator, field coils produce an electromagnetic field and the armature conductors are rotated into the field. Thus, an electromagnetically induced EMF is generated in the armature conductors. The direction of induced current is given by Fleming's right-hand rule. The thumb represents the direction of loss, the forefinger represents the magnetic field, the second finger represents the direction of current. According to Fleming's right-hand rule, the direction of induced current changes whenever the direction of motion of conductor changes. Let's consider an armature rotating clockwise and a conductor on the left is moving upwards. When the armature completes a half rotation, the direction of motion of that particular conductor will be reversed to downwards. Hence, the direction of current in every armature conductor will be alternating. If you look at the above figure, you will know how the direction of induced current is alternating in an armature conductor, but with a split ring commutator, connections of armature conductors also get reversed when the current reversal occurs, and therefore we get an unidirectional current at the terminals. Other than that, Lenz's law can be used to explain the working principle of DC generator. The law states that the direction of induced current is such that it opposes the change of producing it. For example, when the north pole of bar magnet is brought towards a solenoid, the solenoid is magnetized to oppose the magnet. Since north pole repels north pole, the part of solenoid being approached by a magnet will be magnetized as north. Therefore, current will flow in anti-clockwise direction in part of solenoid. Lenz's law is used to determine the direction of induced voltage. The voltage will be induced if the conductor moves in the magnetic field and cuts the flux lines. As a result of this voltage, current will flow through the conductor if the conductor circuit is closed. With the following activity, please use the link below as it may provide you a better idea on how Faraday's and Lenz's law work. It should look like this once you use the link. You should be able to get deflection on the voltmeter as you move the bar magnet into the coil. To increase the magnitude of induced current, the speed of relative motion should increase as well. As I have said, number of turns in solenoid is simply one of the factors that affect the magnitude of induced current. The more the number of turns in solenoid, the greater the induced current will be. This is the principle of Faraday's law. When the magnet with north pole entering the solenoid, the deflection of voltmeter needle is to opposite side, which is positive. Let's change the pole of magnet. The voltmeter needle deflect to positive side with south pole entering first, then it deflects to the negative sides. These two situations can be explained using Lenz's law.
Okay, now moving on, I'm Jackie and I'll be talking about the mathematical equations that are related to the EMF of a DC generator. I'll be talking about mainly three equations, but first and foremost, it is important for us to grab some basic and fundamental concepts and ideas before tackling these three equations. To me, this entire chapter is actually pretty scattered, where one topic just randomly jumps to another topic without any significant relation whatsoever. But nevertheless, let's get right into it. Okay, the EMF or electromotive force that is measured in volts is actually the voltage developed by an electrical source that keeps the current flowing through the conductor. Now, to make things simple, imagine charged particles that move or flow in a conductor. It produces current. Now, here's the catch. To keep the current flowing, some sort of force is needed to, push the current through the conductor, which is what we call electromotive force. What we will be studying is a generator that converts mechanical energy into electrical energy. Do keep that in mind. Now, we have to understand Lenz's law and Faraday's law before advancing to the three equations. So basically, Lenz's law talks about like the end of a coil where the magnet is facing will produce a same pole to the end of the magnet that is exposed to, because an induced current always flows in a direction such that it opposes the change which produces it. Whereas for Faraday's law, basically comes up with an equation to calculate the electromotive force when a coil of wire is moved into and out of a magnetic field, which we have over here. EMF equals negative N multiplied by delta BA over delta T. This is Faraday's law. Okay, the first equation that we are going to sort of go into is the equation for motional voltage or induced voltage, which is actually kind of similar to the equation stated in Faraday's law, but it's presented in a different form. Okay, now we know that magnetic flux equals the magnetic flux density times area. We call it as BA. Okay, adding d over dt to both sides of this equation, we will get difference of magnetic flux over difference of time equals B multiplied by difference of area over difference in time. Okay, deriving from Faraday's law and changing the magnetic flux sign into BA, we will get E equals to NB dA over dt. Now, difference in area also equals to the length multiplied by the difference in displacement. Now, summing all of these things into the equation, we get another new equation for motional voltage, which is E equals to NBLV sine theta. You just need to understand how to derive this equation. Don't need to necessarily remember it, but just understand the entire process. And here's a table to help you to understand which terms belong to which. Okay, moving on. The second equation is the induced EMF of a DC generator. Now, we know that the induced EMF per conductor is EC equals to difference in magnetic flux over difference in time. Okay, look at the table below. EG is what we're going to calculate, which is the induced EMF in voltage. To get an equation in EG, a few steps are required to build up into this final equation. Now, deriving from EC equals delta of magnetic flux over delta time, we will get delta of magnetic flux equals to the number of poles in the generator times magnetic flux. At the bottom of the equation, dt equals to 60 divided by the speed in RPM, and the unit is in seconds. Okay, subbing these two equations into EC and taking EC multiplied by Z over A, which is the total number of armature conductors over the number of parallel paths, we will get a final equation in EG, which is this. The induced EMF of DC generator, EG, equals to the number of poles of the generator times the total number of armature conductors times the flux per pole in Webers times the speed in RPM over 60 times the number of parallel paths. Moving on, the third and last equation will be equation for electromagnetic torque. Now, based on the first slide, generator and motor both produce power, but convert different forms of energy into one another, right? The power generated by a generator would be PD, which equals to the induced EMF times the current, whereas the motor generates mechanical energy, which is electromagnetic torque times the angular velocity, which also equals to PD. Now keep that in mind, we have to find an equation for electromagnetic torque. Now, before subbing both of these two equations together, we have to find an expression for angular velocity, which is 2 pi n over 60. Now, subbing both of these equations together, we will get this final equation for electromagnetic torque, which is Pz times magnetic flux over 2 pi a times current.
Hi everyone, I'm Elise. As you can see, the figure below shows the change of induced EMF when the coil is at different position. The direct current generator produces electric current or voltage based on the principle of electromagnetic induction. So, now I'm going to talk about the relationship between the magnetic flux and EMF. In the equation, phi equals to BA cos theta. Phi represents magnetic flux, B symbolizes magnetic field strength, and A is the area of the loop. Theta indicates the angle between the normal line and magnetic field. When the area and magnetic field strength is constant, magnetic flux changes as the theta changes. When the theta is zero, the magnetic flux is maximum. Since the electromotive force value depends on the rate of change of magnetic flux, electromotive force is maximum when the magnetic flux is zero, as you can see in the graph. When the coil rotates, the angle between the normal and magnetic field increases from 0 to 90 degrees. The amount of magnetic flux decreases from maximum to 0. When the coil rotates from 90 degrees to 180 degrees, the magnetic flux decreases to negative. If the coil continues rotates to 270 degrees, the amount of flux increases from negative to 0. The amount of flux increases to the maximum when the angle between the normal and the magnetic field increases from 270 degree to 360 degree. As you can see that this is the full rotation of a DC generator. At the beginning of the rotation of coil, theta is 0. Therefore, the value of magnetic flux is maximum. When the coil is horizontal, the normal force is perpendicular to the magnetic field. The diagram 1, 3 and 5 apply the same concept as they are all vertical. Diagram 2 and 4 apply the same concept as they are horizontal. The value of electromotive versus time graph are determined by obtaining the gradient of phi against angle rotation graph at that particular instant. For example, when theta equals to 0, the gradient of the phi versus theta is 0. This means that the instantaneous induced EMF will have the value of 0. After half of the revolution, the commutator maintains current in a single direction. Thus, the graph against time is reflected against x-axis. Notice that the direction of current changes every time the magnitude of flux becomes maximum. The amount of flux that passes through the coil decreases from the maximum value to 0.
Hi everyone, I'm Jonah and I'm going to talk about DC generator with 2 or more coils. Now I'm going to show you a few examples of this DC generator. The first one is a 4-coil DC generator and the second one is a 3-coil DC generator. And the last one is a DC generator with more than 10 coils, which is commonly used in industry. So each structure is similar to a typical DC generator but just with extra coils. The commutator is divided into 2 coils, so now there will be 4 segments in the commutator instead of 2, and a new segment passes each brush every 90 degrees instead of 180 degrees during a rotation. Hence, the decreasing current from the vertical coil will be replaced by the increasing induced EMF from the horizontal coil when the common brushes switch between the split rings. So the reason of why this DC generator is used is because the EMF produced by 2 or more coil DC generator will be higher than a single coil DC generator. This can be proved by using Faraday's laws of electromagnetic induction, which is E is equals to negative N multiplied by the change in magnetic flux divided by the time taken. Hence, this clearly shows that the numbers of turns is directly proportional to the electromotive force produced. So when there are more coils, inevitably the numbers of turns of the coil will be higher and the electromotive force will increase accordingly. If you plot the graph of output voltage against the position of coil of a 4-coil DC generator, you can obtain a graph with similar shape. So you can notice that the voltage of a 4-coil DC generator never drops to 0, unlike a 2-coil DC generator. So in this case, when the coil of a DC generator is vertical, the output voltage will be 0. So by using a DC generator with 4 or more coils, it will produce a smoother output voltage compared to a 2-coil DC generator. And also, by putting more coils, you can smoothen the output voltage further to increase the yield of DC output. As expected, this type of generator also comes with its pros and cons. So I will be starting with pros first. So it can overcome the fluctuating output and produce a smoother current. However, it also brings the cons. So the cons is it can cause sparking across the insulating gap, which would be dangerous if there is flammable gas nearby. So now, and lastly, I will be talking about the modification to increase the efficiency of DC generator. So the first modification is using superconductor material to make the coil. This can reduce the resistance and energy loss in the form of heat from the coil. Also, the generator has to be designed with good ventilation and install a cooling system to reduce the heating of the coil. The resistance of conductor increases when its temperature increases. Moreover, you can also use a stronger magnet to produce a greater density of magnetic flux. And lastly, you can use bearing in the generator to reduce the friction between the rotating and stationary part of the generator. And that's all from us. Thank you.